it's very atomic, right? You get a request, you do the processing, you send some messages. So it has the illusion of everything being atomic. Well, it really is atomic at the low level. But those events really represent, in your application, they represent requests and responses. Okay? And now we're explicitly identifying some messages being requests and other messages being responses. So now you're thinking more about the way your application works. And in terms of the way your application works, you send a request to an actor, it's going to do the processing and send the response. But while it's doing that processing, it may need to send requests to other actors and get their responses. Okay? Those other actors may be on using other threads that may be other mailboxes which may be active, and so you're now working across threads. And so what happens is this: you send a request to this actor, it sends a request to a third actor, and the second actor, he gets yet another request from another user. So now, although each message is processed atomically, as long as you look at request messages and response messages, each message is processed atomically, but the overall processing of a request is not atomic, and it's interleaved with the processing of other requests. It's still thread safe. So you don't have thread safety issues, but you do have the problem of, well, while I'm processing this request, I change some things, then I go along and I send a request to another actor, I get a response, and then I want to make some further changes. But in between there, somebody else came in and make a request, and they're going to look at the state, and it's halfway done. So what you need to do is aggregate all your changes until you're to the very end, and then update the state of the actor if you are dealing with situations like that. It puts a little bit of a burden on the programmer. Now there's two ways around that. One way is with the other actor systems. Like I said, they can filter out all the requests that they don't want to deal with, so that they're only deal with a request. They're going to send other secondary requests. They're going to get the secondary responses, and they're not going to get any new primary requests until they're done. With 2.1, I provide you an unblocking lock, so you can effectively do the same thing. So you can guarantee exclusive use of a resource, i.e. the state that you're going to be updating in stages. So you get the same effect. Okay. And finally, decoupling actors and mailboxes. I've talked about this all along. So we've got a many-to-one relationship between actors and mailboxes now. So actors can share mailboxes. The mailboxes are the lightweight threads, and they also handle the asynchronous message passing. So now, we open the door to synchronous processing. We open the door to passing messages using a method call instead of sending a message with a callback. And then sometime sooner or later getting a method on that callback executed and then you have to process the response. So that's the speed ups. So that's how we made it fast.
Yeah, one question.
Yeah.
When you say it is a lightweight thread, and these lightweight threads don't even have their own stack.
Stack, right? Because
So how can you create such a thread in Java?
It just means you have tasks which are runnables.
Okay.
Okay, and you have a thread pool. And so each actor, each lightweight thread is a runnable.
So
And
it's
when you pass it a message, you send that runnable to the thread pool so that it runs. Okay. So the thing that we're guaranteeing is it's a lightweight thread, and that it may be using different real threads at different times. Is all. I mean, it's just a way of thinking about it. It's a valid way of thinking about it. But it's only going to be holding on to that thread with its stack until it processes the messages that it has queued up, and then it's going to just let go. And the program stack is going to start over from the beginning. I mean, you're going to start over from the beginning. The runnable is resubmitted, and you start. So it's just, you're just going to execute some nested methods and then return, and then the next time there's some new work, it just gets rescheduled. But
Yeah, so
it's nothing fancy.
Okay, those are runnable tasks basically.
Yeah, yeah. Each thread each mailbox is a runnable task, which will process all the messages in the input queue. And when it's done, it returns. And then it has to be rescheduled when there's more work. Simple stuff. Nothing fancy here. There's very little fancy here. It's just a slightly different way of thinking about everything. Okay, so now, making things easier to program. I said, we've got a door here that we can enter as soon as we separated out mailboxes and actors, so we can do a lot of synchronous programming. So asynchronous message passing requires callbacks, and this is a little background, and synchronous message passing obviously does not. Okay. Callbacks are a pain. Well, if you're only using a couple of them, they're fine. But, if I'm sending a request with a callback, and then the callback gets called, and then I send another request, and then with a callback, you're nesting, or spaghetti code. You can just define all your callbacks, boom, 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 and you send a request and you pick one, and then you lose the continuity of flow. So either you can have a mess of spaghetti, or you can have highly indented, highly nested anonymous functions, methods, anonymous classes. So it's kind of like your choice. Now, there's ways around that. You can use state machines. I provide you a state machine, really nice composable state machine in Jaxer, if you really want to do a lot of complex asynchronous stuff. But for the most part, you don't have to. The JIT project I'm working on is entirely synchronous. The entire project. There's only one point of asynchronousness, and that is when something gets modified, you need to notify somebody else on some other subsystem that the data is now dirty and has to be written to disk at some point if you're implementing a database using the JIT project. And for that, you cannot, if you're in the middle of a synchronous routine, you cannot do something asynchronously, because by the time you get the result back, you may have already returned. So the results of an asynchronous call cannot be used in the return of a synchronous method. It just, as soon as you go asynchronous, your control flows and your data flows part ways. But you can still do a one-way event, okay, which is asynchronous, but there's no callback, right? So hey, so I've got this library, and at some point I will put in the notification of the structure is dirty, and that's an event, a one-way message. So I support those as well as two-way messages for good reason. Okay, so now just to focus very narrowly here on, I'm almost done. I'm really almost done with these slides. And I don't like watching other people's slides, so I have a lot of sympathy here. Sending a request. When sending a request to another actor, a callback is used to receive the response. For asynchronous responses, the callback is invoked after the method that sent the request returns, but on the same thread. I mean, we're going to maintain thread safety. But for synchronous responses, if you call something and you get a synchronous response, and all the code here actually, even when you think you're doing asynchronous, it's doing synchronous, except when you absolutely force it. The synchronous response, the callback is invoked immediately as soon as you've completed sending the message. So you don't know when this response is coming back. It's going to come back sooner or later. And so, for example, if you're working with a cache, okay, you want to get something. So get me this item N. Okay, so you'll get a synchronous response. It's an asynchronous send to an asynchronous service, but the response is going to be immediate. Synchronous response, because it was in the cache. Boom, boom, right? If it's not in the cache, you may have to walk across the network to another computer running in the Google farm, or God forbid, you might actually have to do some disk I/O if it's not on, in memory and it's not on the computer. So the response will be, a long time after. Okay, so that's sending a request. Sending a response, and of course we have to talk about sending a response in terms of an actor that has received a request. Okay, so when a request is received by an actor, you also get the callback. You use the callback to send the response. Okay. Now I have a rule. It's weakly enforced, but it's what makes sense, and that is that exactly one response is given for every request. Now, if an exception is raised, I track those exceptions and treat them as responses. So still, it's and the reason why I have to enforce I enforce this weekly. In other words, I check if there's a request and you've sent a response or you got an exception, you cannot send a response. It will be bit bucketed. And the reason why that's important is because I support a lot of parallel programming. So if you get a request and you send out 100,000 requests to other actors, and then you aggregate those responses, and when you get all the responses back, then you send the aggregated response back up. Or maybe you're just interested in the first response, or the first response that meets some criteria, and then bit bucket the rest. Or but what happens if on the third you're aggregating these responses, and on the third response you throw an exception, you return that as the response, and then you get another response. That'll be bit bucketed. So only one response per request. Callback sent by the source actor with a request is not the same, typically, as the callback received by the actor that's going to process that request. Because we're maybe moving between threads. And so, we're going to have to, that callback is going to have to handle getting the response executed back on the correct thread. So that's where the intermediation is. That's where the games are, is in the callback set that is handed to an actor when it's handed a request. It's not just the callback that you sent. Okay, so now 4 slides left. 4 slides left. Okay.
Do you have any pictures showing the same thing that you did? I can do whiteboard if you want. We can talk about some things there. I'm not real strong on picture tools.
Okay. One novice question about the previous slide. These callbacks would be interfaces. Will be?
Yeah. Well, actually, I have a class and you subclass them.
Okay.
It's a class with one anonymous method.
All right.
Or maybe it's an interface. I forget. No, I think it's because it used to have another method. So
right.
It's close to an interface. Yeah.
So you kind of serialize the entire the callback also is part of the message and
So no serialization here.
So I mean
That's another project.
no, I mean I was just curious that if the callback is the callback part of the message itself, the original message that goes over?
I keep the message and the callback separate. For one thing, this allows me to do what is very strongly promoted in functional programming, which is, and in actors in general, which is that your request should be immutable. This allows you to send the same request to multiple actors. And then, it doesn't get, you don't allow for it to be changed. So it gives, it saves you from that bug, that obscure bug, that you did 3 o'clock in the morning when you sent the same same message to 2 different actors, and one of them changed it and the other one got the change when it shouldn't have. I like, in principle, I like this idea of immutable. I don't enforce it as an application developer. I wouldn't always follow it, but it's nice just to separate the callback. The callbacks change in the process of passing the request and the callback. The callback is replaced. It ends up getting wrapped at least once. Okay, So, I'm glad I went over those details. So, now we're talking about the three types. Three special cases here. And why on earth the three special cases? And I'll tell you why. It's because I don't like all the garbage in my code. I don't like all those callbacks. I would much prefer to keep it simple and just do method calls. So I've come up with three special cases here. Synchronous requests, initialization requests, and concurrent requests. And they each have different rules in terms of who has to worry about thread safety. But they can all be called synchronously. They can also be sent as messages asynchronously. But the receiver is going to think that they're, it doesn't matter how they're sent, they're going to be received the same way as synchronous messages with no callbacks. So when you get one of these guys and you're processing it, you cannot, as I was saying before, you cannot then send an asynchronous request to some other actor. Not if you want to be able to use the results right away. Okay, so let's talk about these. First of all, synchronous requests. An actor can call another actor with a synchronous request only if both actors share the same mailbox. Otherwise, the request must be sent with a callback. But that, like I was saying, the callback isn't going to be given to the receiving actor. Synchronous requests, like asynchronous requests, are processed by the actor with full thread safety. Okay, there's no cheats on this one. But unlike regular requests, synchronous requests are atomic because method calls are atomic. You call something, there's no thread swapping or anything. There's no interleaving of other requests. It's an atomic process.
But if the mailbox is actually shared between actors, so there should be
They have
consistency
mailboxes shared between actors, but then it's a single thread. So that doesn't break anything. It's still a single thread. It's not, the only time you have a problem is if an actor is using more than one mailbox. Then, sometimes some of the code will be running on one thread and some other code working on another thread at the same time, and you've broken thread safety, and happy debugging after you reach production.
In that case, you have to be responsible for your data.
No, you don't do that. You don't do that. That's not actors. Okay, so synchronous requests are very simple. I just restrict you. You're not allowed to do, when you're processing a synchronous request, you cannot do an asynchronous request. And synchronous requests, if you happen to be running on, if you know that you're in the same subsystem, then your application code can go, oh, let's just use a method call. So, you can't always use a method call because you don't always know. You can always send, but if you know the application of the subsystem that you're coding for, then you can do synchronous processing, method calls with synchronous requests. And this is just a type of request. I've got a request, the base, and then you've got subclasses under that. One of the subclasses is a synchronous request. And processing is based on what type of superclass you're using. Okay, second of three is the initialization request. This is where we allow you to break thread safety all over the place, and we don't care. And the reason why we don't care is because it's an initialization request, which is to say, an actor only receives initialization requests when it's being initialized. When you initialize an actor, what's happening? You've got one other actor that's driving the initialization process. Okay, so you're single-threaded, not single-threaded from the perspective of the actor that's receiving the request, but single-threaded from the perspective of the actor that is sending the request. So you don't have to worry about thread safety. That's the application developer's problem. If the application developer decides he's going to have multiple actors running on separate threads trying to initialize the same actor, he's crazy. Just don't do that. It's a very simple restriction, and it opens the door to doing a lot of things that are not thread safe, but because of the way you're doing it, they are thread safe. So this way, because of this means that you can use method calls for doing all your actor initialization, which is a really nice thing. Okay, and then the third one, you've mentioned concurrency. You can use concurrent data structures within the state of your actor, no problem. And you can tag, and you can have, you can subclass your requests from the concurrent request class so that the framework knows that you're doing a concurrent request, and then it's not going to worry about thread safety. It's the processing of a concurrent request must be thread safe. That's the application's problem, application developer's problem. And it's, you know, most things are not going to be concurrent requests, but if you have the processing of a request only accessing immutable data, you know, like you have some string that isn't going to change, and you want to get the value, okay? Immutable data, a string, get the value, that's a concurrent operation. And of course, there's, you know, there's a whole library in Java, util concurrent, that gives you different things that you can use. So this gives you more power, more things that you can do with method calls without having to worry about callbacks or asynchronous processing. And that's why, you know, I developed this shortly after starting work on the JIT project. Because I'm looking at this JIT project, and you know, it's the third implementation. I'd always done it with everything asynchronous. Well, the second implementation was asynchronous. The first implementation wasn't even threads. But this time around, I wanted to go back to just very simple, straightforward code. And I could do it with these 3 special cases of requests. So now I can create nice subsystems that are fully synchronous, much easier to debug than asynchronous code. And I just love working with this. Okay, that's the slide. I could do a few more hours things. I don't know how long you want to sit here, but let's look at some code. Okay, let's look at some code now. Again, this takes you to this takes you to my examples, and we might get into this maybe another talk. This is programming by example, so this is a real nice tutorial, but I promised you guys some real code. So let's instead look at the heart of the beast, okay? And I've got 2 packages that are the heart of the beast, the concurrent and the events. This is the low level stuff, okay? This is where it gets real. And there's 2 packages, and each one contains a bunch of interfaces and 1 class. So today I'd like to take a look at the thread manager, my alternative thread pools. Now, you know, I've known for a long time that the libraries that are provided with the JDK are second rate. You know, there's a lot of specialized libraries out there. I think the best example is Joda. Have that right? The replacement for Java time date. Nobody in their right mind uses the JDK's time date library. Joda is so much easier to use and much more comprehensive. But, you know, despite my past experiences, I'm probably like the rest of you guys, and, you know, thread pools? Are you kidding? I'm not going to write a thread pool. You know, that stuff, that's got to be black art. That's got to be magic in there. They did something really, really neat and fancy and super. I was wrong. Thread pools are slow. Now, I can justify why they're slow, and it's because they're old. And, you know, these days we've got things like concurrent data structures that were not in the earlier versions of the JDK. So we can do a really high performance implementation of thread pools. Very little code, very fast, very, very simple. This is a very nice technique. So I'm restricting the problem. Thread pools, there's so many different ways they operate, right? I'm just picking one, and that is I've got a fixed number of threads, and I've got some runnables that I want to run. Okay, I'm not going to dynamically increase or shrink my thread pool. This is just something very simple. Because I don't need that many threads, so, you know, being able to dynamically increase and shrink it is not critical, because with a small number of threads, it's not using up that much resource, so, you know, this should be adequate. And for me, it is. Now, the key here, the heart of the matter, is right here. This is it. Okay? That's the heart of the matter. So you want to process some task. And the way you process that task is you do two things, and the order is important. The first thing you do is you add that task to a list of tasks to be executed. And the second thing is that you release a semaphore. That's it. Okay? So let's look at those data structures. I can find them. Okay, so task request, that's your semaphore. And you can release any number of semaphores. So you can have any number of threads that are requesting tasks at the same time. So each one of them just adds the task to the queue and then raises a semaphore. I mean, at some instant, you might have 3, 5, 10 semaphores raised. Very unlikely. Generally, it will either be 0 or 1. And the first thing you do is you add it to the task, and the tasks is a concurrent linked queue. And this is the only time I use a linked queue. The linked queues are very slow for multi-threading. You always want to use arrays. I think except in this case. So this is a very different usage of a queue. Because what's happening is it's a many-to-many. You've got many threads that might want to be submitting tasks, and you've got many threads that are waiting for tasks. So it's very, very concurrent situation. And now we should look at the logic for how this all works. Now remember, we always put something in the thread queue before raising a semaphore. Okay? And I've got a cheat in here that leverages that. There's the code. So run, this is what a thread does, a thread in the pool. So the first thing it does is it acquires a semaphore. It's just gonna hang there waiting for a semaphore. Once it gets the semaphore, we'll skip this. It pulls the thread, the queue. It pulls the queue. Now, we know that queue has something in it because, for every semaphore, we first put a task in the queue. So if we've acquired a semaphore, that means we know there's a task waiting for us. We don't have to check for null. Okay? Now, and I will point out that we're using this concurrent queue, this concurrent linked queue, and concurrent linked queue never blocks. So you can only pull. But I only pull when I know there's something there. And that's it. Once you get it, you run it. Bada bing. That's my thread pool. Okay? Now, if you want to make it complicated, I've got this closing flag. Okay? So after I get a semaphore, I check to see, hey, are we shutting down the system? If we're shutting down the system, then exit the thread. Okay? And then we've got, the usual fancy schmancy logic here. For the close, first thing we do is we flood it with a whole bunch of semaphores, and then we do our joins. Oh, well, first of all, we set closing to true. So we close it, we flush everything out with a semaphore, and then we do the joins on all the threads. And so, this is the complicated logic. So that's a fast thread pool. I don't think you can beat it. You may be able to beat it, I don't know. I know with Akka 2.0, they were talking about, they came up with some complex thing with striping and this and that because they found that the thread pool technology they developed at that point didn't scale over 8 hardware threads. Well, I don't have an environment for testing that. If somebody has a T4, I'd love to see if this scales. But till then, it just have to wait. But I think it should scale. I have a feeling it should scale, but when it comes to multi-threading, feelings count for naught. Where you develop the best intuition you can, and then you benchmark. And then you get surprised, and you refine your intuitions. It's an ongoing process. This is one of the things I like about the actor model, is it's much more predictable. Okay, so I could go on for another 3 hours. I'll probably lose my voice in the process. I'm noticing I'm a little weak now, but or I can come back some other time if you want me to talk again. I've got this lovely this lovely tutorial on how to actually write code that uses this step by step. It's very nice. Oh, did I ever turn that on?
Okay, I'm just.
No, I'm asking. I don't think I turned it on.
Yeah, it
No, I did.
You did. You turned it on. That's why I turned it on. Okay, fine. Marvelous.
What tools did you use for benchmarking?
JUnit. It's my other project. Okay. So we'll see if we can't send you a copy of this.
Yeah, sure.
Any questions?
There we are using closing is equal to true, which is actually accessed in multiple threads, which is not actually atomic.
It's only set in one thread. Actually, it might be set in a multiple thread. You might be. I mean, let's say it's false when you start the program, and at some point it becomes true. You might have doing multiple closes at the same time, but having multiple threads setting the same variable to true, I don't think is very harmful. Just as flushing everything out with more semaphores. If you get another thread giving even more semaphores, that's fine. I don't know about the join though. It might be a problem. I wouldn't recommend doing more than one close. Maybe it should be synchronized.
No, there is atomic boolean actually in concurrent packages.
Oh yeah, but that would be overkill. Okay, I've got the other piece of code that I've got that I can go over next time. I always like to go over some code. I mean, my God, slides. And it won't be slides next time. I'll just go over the wiki. The other piece of code is the heart of the mailbox, which is basically nothing more than a queue. Again, I think it's a linked list because it's a linked list of array lists. That's where I get around the problem of using linked lists, because they're things that are linked together are big, or can be big. Rather, under load they're big, which is when you need them to be big. And that's where I have the logic for preemption, which is just an atomic reference. It's so simple. There's nothing fancy about this. There's just a lot of it. Layers and layers and layers of abstraction. So, it's a paradigm shift for the paradigm shift for the paradigm shift for the. Which is why the programming by example, how to program this by example, is really helpful. Otherwise, forget it.